Hi, this lesson is about integration by parts, which is another very important technique of integration. And you can see right at the top here, I have a formula for integration by parts, and this formula comes from the product rule of derivatives. Let me do an example to show you how we can use this formula. Let's take a look at this integral. X times the cosine of x. And we'd like to get an antiderivative of that thing. In the integration by parts formula, you notice that this integral over here on the left matches our integral. So what we need to do is figure out what that u is and what that dv is. U is going to be, in this case, our x, and dv is going to be the cosine of x times dx. Now you'll notice on the formula over to the right, we're going to need to find v and du. So let's go ahead and do that. So u is going to be x, and dv is the cosine of x dx. Now, to find v, we're going to integrate this formula. And let's see how that works. Okay, now how do you integrate dv? Well, this is really 1 times dv, right? And the antiderivative of 1 with respect to the variable v is going to be v. And on the right-hand side, the antiderivative of the cosine of x is, of course, the sine of x. To get du, it's the same as if getting du with substitution. So du is going to be dx. Okay, now we can plug everything in to our integration by parts formula on the right-hand side. So it's u times v, x times sine x, minus the integral of v times du, which is sine of x dx. And the antiderivative of the sine of x is cosine of x. So we get x times the sine of x minus the negative cosine of x. And those two negatives pair together to give us a positive. So here is the antiderivative of x times the cosine of x. And you might want to just try taking the derivative of this and checking to make sure that you really do get back to x times the cosine of x. Okay, we'll do another example in just a minute. Okay, let's do another example of integration by parts. This time we're going to get the antiderivative of x times the natural log of x. And this time I'm going to let u equal the natural log of x. And dv is going to be the rest of it, which is x times dx. Okay, then du is going to be 1 over x dx. And recall from the previous example, to get v, we took the antiderivative of this equation. So v is going to be 1/2 x squared. Okay, now let's just plug into the integration by parts formula. U times v is going to be 1/2 x squared times the natural log of x minus v times u. So it's the integral of 1/2 x squared times 1 over x dx. And we can simplify this integrand here. Let me just copy the whole thing. 1/2 x squared natural log of x. And we can pull that 1/2 out of the integral. And x squared times 1 over x is just x. And the antiderivative of x, of course, is 1/2 x squared. Oops. So we get, let's fix this, 1/2 x squared ln x minus 1/2 times 1/2 x squared, which becomes 1/4 x squared. So our final answer is 1/2 x squared ln of x minus 1/4 x squared. And there's the antiderivative of x times the natural log of x. Now, you're probably wondering why I picked u to be the natural log of x this time, when in the previous example I picked it to be x. Well, that's what this Slighty thing is up here in the upper right. This is how you choose u. The best choice for u is up here at L for logarithmic. Second best choice is I for inverse trig. Next is algebraic, which was what we chose in the first example. The fourth best, or the second worst, is trigonometric functions. And the absolute worst choice for you is exponential functions. And if you go by this rule of Slighty, you'll never go wrong on your choice for u. Okay, that's it for this example. Let's go on and do another example. Let's take a look at another example of integration by parts. Okay, let's look at this integral. X squared times e to the x. And if we go by Slighty, I'm going to let u be that algebraic part, the x squared. dv is going to be e to the x dx. du is going to be 2x dx. And the antiderivative of e to the x is just e to the x. Okay, so we plug this into our integration by parts formula, and we get u times v, which is x squared times e to the x, minus v times du. So 2x e to the x dx. Now, we got a slight problem, because this integral is now another integration by parts integral. So let's go down here and take care of this integral. 2x e to the x dx. So again, I'm going to let u be that algebraic part, the 2x. dv is e to the x dx. du is going to be 2 dx, and v is e to the x. Okay, so we plug this into the integration by parts formula, and it's u times v, so it's 2x e to the x minus the integral of v times du, 2 e to the x dx. And I could pull this 2 out of the integral. So I get 2x e to the x minus 2 times the integral of e to the x, which is just e to the x. So we get 2x e to the x minus 2 e to the x. Okay, now we're going to go up and replace this integral with all of that. Okay, so we get x squared e to the x minus parentheses 2x e to the x minus 2 e to the x. And if we take away those parentheses, we get x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And that's our answer. Now, you'll notice that we had to do integration by parts twice on this integral. And why was that? It's because the original integral had an x squared in it. Every time we did integration by parts, we knocked that exponent on the x squared down by 1. If that had been an x cubed, we would have had to do integration by parts 3 times. And after we had finished all 3, we would have to backfit into the previous one. And you can see that this can become a lot of work. But there is a shortcut for this. There is a shortcut when that u is algebraic. And that's called tabular integration. And we're going to do that next. Okay, let me show you how tabular integration works. And we're going to use that same integral we did in the previous example, x squared e to the x. And if you remember, in the previous example, this took us 2 iterations of integration by parts, because each iteration decreased that exponent on the x by 1. And it took us about 5 minutes to get through this integral. Tabular integration is much faster, but it can only be used when that u is an algebraic term like that x squared. Let me show you how tabular integration works. Okay, we're going to make 2 columns. A column for u and a column for dv. And we're going to pick the u and dv the same way we did in the previous example. So u is going to be x squared, dv is going to be e to the x, and we're going to leave off the dx this time. Okay, now down the u column, we're going to take derivatives. And down the dv column, we're going to take antiderivatives. Okay, so this will be quick. Derivative of x squared is 2x. Oops. 2x. Derivative of 2x is 2. Derivative of 2 is 0. And we stop as soon as we hit 0. Then on the dv column, we take antiderivatives. Well, the antiderivative of e to the x is just e to the x. So these are going to be pretty simple. It's just e to the x, e to the x, e to the x, and we stop as soon as we're level with that 0. All right, then we're going to draw diagonals. And we're going to mark these diagonals starting with a plus, minus, plus. We just alternate plus, minus, until we get to the last diagonal. And we're basically done. There's our answer. On the first diagonal, we have a positive x squared times e to the x. On the second diagonal, a negative 2x times e to the x. On the third diagonal, we have a positive 2 e to the x. And we put on a plus c, and we're done. There's our antiderivative. And if you want, you can compare this to the antiderivative we got in the previous example. You see, it's much quicker doing tabular integration. Okay, well, that's it for tabular integration. Let's do another example of integration by parts. This particular example is going to illustrate a type of integration by parts called circular integration. So let's look at this integral. E to the x times the sine of x. And let's get an antiderivative. So if you remember Slighty, that exponential function is the very last thing you want to let u equal. So we're going to let u be the sine of x. And dv is going to be e to the x dx. So du is going to be the cosine of x dx. And v is the antiderivative of e to the x, which is e to the x. Okay, let's plug into the integration by parts formula. So it's u times v e to the x times sine x minus the integral of v times du. So minus the integral of e to the x cosine x. Now, this integral we wound up with, e to the x cosine of x, that looks a lot like the integral we started with. So let's go down here and work on that integral. And again, we're going to have to use integration by parts on that. Okay, we're going to let u be the cosine of x and dv be e to the x dx. Du is the negative sine of x and v is e to the x. Okay, so let's plug into the formula. We got u times v, which is e to the x times the cosine of x minus the integral of v times du. So it's minus the integral of e to the x times negative sine x dx. And we can pull this negative sign out and make that a plus sign. So we get e to the x times a cosine of x plus the integral of e to the x times the sine of x. Now, look at what we've got. This integral we wound up with, e to the x times sine of x, is exactly the same as the integral we started with. So let's plug all this back in up here. So our original integral is going to be e to the x sine x minus e to the x cosine x in parentheses, right? Because there's a minus in front of that integral, plus the integral of e to the x, oops, I forgot my x down here, e to the x sine x. And when I distribute this negative sign here, I get, here, let's write it all out. My original integral is equal to e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x. Now, you'll notice we've got the integral of e to the x sine x on the left, which is what we started with, and on the right we've got minus the integral of e to the x sine x. How are we going to handle this? Well, here, let me put a little boundary along this. Oops. So we don't get it confused. So what I'm going to do is I'm going to add this integral to both sides of my equation. This is just a simple algebra trick. And when I do that, I get 2 times the integral of e to the x sine x on the left. On the right, these two are going to cancel, and I get e to the x sine x minus e to the x cosine of x. And we're not quite finished yet, because now we have to divide both sides by 2. And since I'm running out of space, let me see if I can slide this up. There we go. And let's just divide both sides by 2, or multiply both sides by 1/2. So our final answer is the antiderivative of e to the x times sine x is 1/2 times e to the x sine x minus e to the x cosine x plus c. And we're finished. Okay, for our last example, we're going to do an integral that's going to require a combination of substitution and integration by parts. So let's take a look at this. X cubed times e to the x squared. Now, if you were thinking of doing substitution on this, you would probably let w be x squared. Then the derivative of that substitution, the derivative of x squared would be 2x. But that's an x cubed out in front, not an x. But this is still going to work. Let's see how this looks. So we're going to let w be x squared. dw is going to be 2x dx. And 1/2 dw is going to be x dx. Now, here's the trick that's going to make this work. I'm going to take that x cubed and I'm going to split it up. I'm going to leave an x squared there, then times e to the x squared. That extra x I'm going to slide back here next to the dx. Now, look what we've got. That x dx is right there, and that x squared is right there. So let's replace everything. That x squared is going to get replaced with a w. That e to the x squared is going to get replaced by e to the w. And that x dx gets replaced by 1/2 dw. And if you want, you can slide that 1/2 out to the front of the integral. So you get 1/2 times the integral of w e to the w. Okay, now you should recognize this integral. That's integration by parts. And as a matter of fact, we can actually use tabular integration on that. Let's go down here and use tabular integration on this. Okay, so let's just put a little boundary here. And let's do tabular integration on w. Whoops, I left off my e to the w. Let me fix that. It's w e to the w. Okay, so my u is going to be the w, and the dv is going to be e to the w. And if you remember how tabular integration works, down the u column we take derivatives. So the derivative of w is 1, derivative of 1 is 0. Down the dv column we take antiderivatives, which would be e to the w, e to the w. Then we draw diagonals. And we start marking the diagonals plus, minus, plus, minus. And there's the answer. It's going to be positive w times e to the w minus 1 times e to the w, or just minus e to the w. So that's what this integral, is going to become. It's going to be 1/2 times w e to the w minus e to the w. But now we've got to go back to our original variable, which was x. And how are we going to do that? We're going to do that by using our original substitution, w equals x squared. So for our final answer, we get 1/2 times x squared times e to the x squared minus e to the x squared plus c. And there's our antiderivative.